Hello, my dear friends. Welcome to my channel ADC Max. This is your AD Chandrasekharan. In this video, we are going to discuss about the second type of contour integration over semicircle. The type 1 is contour integration around a unit circle. This is over a semicircular contours. For this type, we are going to apply a lemma named as Cauchy's lemma. The first statement is in general over the circle mod z minus a is equal to r. Mod z minus a is equal to r. A is the center of the given circle and r is the radius. Now suppose the radius tends to infinity, what happen? That is the statement of the Cauchy's lemma. Let us see the statement. If the function f of z be analytic as well as uniform continuous function such that mod z minus a into f of z tends to 0 as mod z minus a tends to infinity. That means that the radius tends to infinity, then mod z minus a f of z tends to 0. So once this value tends to 0, then integral over the circle C f of z dz also tends to 0. Now we are going to consider the center as the origin, so that the above Cauchy's lemma about the origin, it becomes, so the point is now origin, the center is now origin, so the circle becomes mod z is equal to r. What is r? R is the radius. Got it? And my circle C becomes now upper semicircle only. Let us see. When the radius tends to infinity, so that mod z tends to infinity, then mod z into f of z tends to 0. What is f of z? The same. It's analytic as well as uniform continuous function. As the radius tends to infinity, then mod z f of z tends to 0, so that integral over c f of z dz tends to 0. What is c here? Here the c is upper semicircle. Upper semicircle. That is upper half of the plane. So this is the second type, contour integration over semicircle. Got it? Let us see how to proceed the problems under the semicircle type. So the working procedure or the rule for this type 2 is, now the given integral is of the form integral minus infinity to plus infinity p of x by q of x into dx. What is x? X is the real part of z, isn't it? So let us consider integral over c f of z dz, where c is nothing but a positively oriented semicircle gamma. See that in this figure, gamma above the real axis. Above the real, what is the real axis? Means z is equal to x plus iy. So the real part of z is x. So above the x axis, that is upper half of the plane. So with the radius r, so mod z equal to r, that means that imaginary of z is greater than or equal to 0. What is the equation of x-axis? Y equal to 0. Remember? So what is the imaginary part of z? Y. So that is mean that. So y is equal to 0 and greater than 0 above the real axis, that is upper half of the plane, together with the line segment, that is the bounding diameter L, with the closed interval minus r to plus r. Minus r to plus r is the line segment. So my circle C is nothing but the semicircle gamma above the real axis in the upper half of the plane plus the line segment with the bounding diameter minus r to plus r. So this is my gamma, that is this is my C. This is my C. So here the only singularities of phi of f of z in the upper half of the plane. So they are called the poles. They are called the poles. Now what happened? This integral over C f of z dz is the sum of the integral over gamma plus the real line, that is the line segment minus r to plus r. So that when the function f of z has singularities on the real axis alone. What's the real axis means? This is the real axis, right? This is in the real axis. What's the real axis? Here x is the real axis. What is x equal to 0 represents? Y axis. X equal to 0 represents y axis. So the singularities of f of z on the real axis, that is upper half of the plane, then integral over C f of z dz is equal to integral minus r to plus r. See the direction? See the direction mark? We start from minus r. Let us move along the line segment up to r. So integral minus r to plus r, it is on the real axis. So that it is f of x dx. This is the x-axis, you know. So f of x dx. Then from r again travel around the gamma, come back to the minus r. So it is single curve, simple curve, closed as well. It has some orientation. Got it? So once I repeat this, here my C is nothing but integral minus r to plus r along the x-axis. So f of x dx plus the integral over the curve gamma, that is above the x-axis upper half of the plane, that is integral over gamma f of z dz. So integral over C is sum of minus r to plus r plus gamma function. Minus r to plus is a real axis, so it is in terms of x. This is my equation number 1. But we already know the Cauchy residue theorem. With the help of the Cauchy residue theorem, we know integral over C f of z dz is nothing but 2 pi a into sum of the residues of f of z at its poles in the upper of the plane. See that upper half only. Don't consider the negative one, upper. So positive poles only we consider. Right? This is called semicircle. Okay, that to the upper half only. Clear? Now setting the radius tends to infinity. What happened? The radius tends to infinity means this is minus infinity, this is plus infinity. That means the gamma, what happened? This upper circumference semicircular region, it is completely fell onto the axis. So that is the Cauchy's lemma, says that as the radius tends to infinity, mod z tends to infinity, because this is a circle whose center is the origin, radius is r. Now the radius tends to infinity, this circle mod z, that is the upper half of the plane, tends to infinity, so that f of z tends to 0. Once f of z tends to 0, integral over this gamma f of z dz is equal to 0. This is by using the Cauchy's lemma. So once this gamma value is 0, let us substitute this in the equation number 1, then becomes integral over c f of z dz is equals to integral minus infinity to plus infinity. Why? Because r tends to infinity. So minus infinity to plus infinity f of x dx. So over the semicircle above the upper half of the plane, it becomes the real definite integrals, that is indefinite integrals, minus infinity to plus infinity f of x dx. So this is the complete idea behind this type number 2. Got it? Let us see the problem. You can easily understand this second type. So the problem in the type 2 contour integration, this is the problem using contour integration. Evaluate integral 0 to infinity dx by x squared plus a squared to the whole square. So type 1, do you remember? It is theta, cos theta, sin theta, d theta, but there is no theta here, only the real x. Clear? So this is comes under the second type under the contour integration. Okay, now let us consider integral over c f of z dz is equal to integral over c, whatever we have in x written in terms of z. So dz by z squared plus a squared to the whole square. So this is my f of z. Got it? 1 by z squared plus a squared to the whole square. Here what is my c? Here my c is the semicircle gamma. See the gamma above the real axis. Above the real axis. That is, it is lies in the upper half of the plane bounded by this diameter minus r to plus r. What is r? R is the radius of the circle. Got it? So integral over c f of z dz is equal to integral, we start from minus r, let us travel through this real axis up to r. So integral minus r to plus r, it is the real axis, so that we written in terms of x, f of x dx. On the real axis, what is the equation of real axis? X axis, y equal to 0. So that's why this only in terms of x plus this gamma curve. This gamma curve, so integral over gamma f of z dz. So this is my equation number 1. So in this equation number 1, we have to calculate some values, but before that I would like to proceed the left hand side, because left hand side is familiar for us. By using Cauchy's residue theorem to get the left hand side value, then by using the Cauchy's lemma we will get the required one. Let us see the left hand side first. What's the left hand side? Yeah, now to find, I named the left hand side I is equal to integral over c f of z dz. The poles of f of z are nothing but the solution of the denominator equal to 0. Clear? Got it? So what's the denominator here? Z squared plus a squared to the whole square equal to 0. That is z squared, I think it looks like a squared minus b squared. So can I rewrite this by a squared minus b squared form? So z squared minus ia whole squared. What is I squared? Minus 1. Minus or minus plus. So ia whole squared to the whole square is equal to 0 is nothing but z squared minus ia whole squared equal to 0 of order 2. Double pole. Order is 2. Now this is looks like the form of a squared minus b squared. So what is a squared minus b squared? A plus b into a minus b. So z plus ia into z minus ia equal to 0 of order 2. So by that way we get z equal to minus ia and z equal to plus ia of order 2. But out of these two poles, z equal to plus ia only lies in the upper half of the plane. Okay, what is z equal to plus ia? Plus ia means what is the point? 0 comma plus a. So where is 0 comma plus a? It is on the positive y-axis. What about the second pole? Minus ia. That means 0 comma minus ia. There is 0 minus ia. Otherwise, the point is 0 comma minus a. That means below the x-axis, negative side of y-axis. So probably the point may be lie below the x-axis here. That means we can consider, no, we won't consider this negative pole because we only consider the upper half of the plane poles alone. So here among these two poles, z equal to plus ia, the positive poles alone considered. Now let us find out the residue of f of z at z is equal to ia, and here the order is 2. Let us use the formula. As we know that limit z tends to a of order n is 1 by n minus 1 factorial d by dz of n minus 1 z minus a full power n into f of z. Here the order is 2, so when I substitute n equal to 2, we need to differentiate only one time. 2 minus 1 is 1, 1 factorial is 1. Okay, here the pole is ia, substitute ia, so z minus ia n equal to 2, f of z we can rewrite in terms of two linear factors so that the respective pole term get cancelled. Z minus ia whole squared, z minus ia whole squared. So the balance is 1 by z plus ia whole squared. We need to differentiate one time with respect to z. What is 1 by x squared differentiation? Minus 2 by x cube, isn't it? Here x is nothing but z plus ia. So minus 2 by z plus ia whole power 3. Now apply the limit z equal to ia. Ia plus ia is 2ia power 3. So 2 cube is 8. So 1 2s are 2, 8 get cancelled. So 4 I cube. What is the I cube value? Minus I. So this minus or minus becomes plus, only 1i and a cube. So the residue of f of z at the pole z equal to plus ia of order n equal to 2 is 1 by 4i into a cube. 1 whole divided by 4i a cube. What about z equal to minus ia? That is, we don't consider because it is the lower half of the plane. Now by Cauchy's residue theorem, we get integral over c, that is my I, f of z dz equal to 2 pi I into sum of the residues of f of z at each poles in the upper half plane. In the upper half plane. So here only one pole and the corresponding residue value is 1 by 4i into a power 3. I get cancelled, 2 get cancelled. So pi by 2a cube is the left hand side value. Now let us putting or assuming that the radius tends to infinity in the equation number 1 by Cauchy's lemma, as the mod z tends to infinity obviously when the radius tends to infinity, so that f of z tends to 0, so that integral over the gamma f of z dz equal to 0. So now I would like to use the 2 and 3 in the first equation. That means we get integral over c f of z dz is equal to integral, what is r here? R tends to infinity. Got it? R tends to infinity. What about the gamma value? Over the around the gamma 0. So this becomes integral minus infinity to plus infinity f of x dx because it is about the real axis. Now this is f of x, that is our question. So dx by x square plus a square the whole square is equal to the left hand side value. By using the Cauchy's residue theorem, we obtain pi by 2a power 3. Pi by 2a power 3, that is what we obtained by using the Cauchy's residue theorem, isn't it? So this is the integral minus infinity to plus infinity, but my requirement is 0 to infinity. So this is nothing but a function with having the even degree. It is called even function. Once it is even function, by using the property, we may write minus infinity to plus infinity as twice the time 0 to plus infinity. Okay, so this 2 comes down here, we get pi by 4a cube, left hand side 0 to infinity, integral 0 to infinity dx by x square plus a square to the whole square. The answer is pi by 4a power 3. A is the positive constant. Got it? So this is the answer. Suppose the given question is minus infinity, means we stop up to this. Clear? So this is the type 2 contour integration over semicircle. The only idea is by using Cauchy's lemma, integral over gamma f of z dz is becomes 0, and by setting the radius tends to infinity, then it is on the real axis. So integral over c f of z dz is nothing but integral over f of x dx, integral from minus infinity to plus infinity f of x dx is nothing but the real indefinite integral. So this is the main concept behind this problem and behind this type number 2. I hope if everyone you may understand in this example. You also try some more problems under type number 2, contour integration over semicircle, only the real variable x. So few problems for your practice. Using contour integration, evaluate the following integrals. Integral minus infinity to plus infinity x squared minus x plus 2 by x power 4 plus 10x squared plus 9. What is the degree of the denominator? 4. So there are 4 roots probably. So these are the 4 poles. The complex roots occurs always in conjugate in pair. That is right. So first 2 poles are plus or minus I, second 2 are plus or minus 3i. But among the 4, we only consider the positive poles because those poles are lie in the upper half of the plane. So we neglect the negative poles. Clear? So consider the positive poles by using the Cauchy's residue theorem as well as the Cauchy's lemma. You may find the answer. The answer is 5 pi by 12. The second one is the general problem. Once again, integral minus infinity to plus infinity x squared by x squared plus a squared into x squared plus b squared dx, where a and b are positive constant. Yeah, once again there are 2 roots in terms of a, 2 roots in terms of b. So this is a hint for you, plus or minus ia plus or minus ib. Once again, consider the positive root alone, plus ia plus ib, because these poles only lie in the upper half of the plane, right? So the final answer, pi by a plus b. A and b are positive constant. And third one, 0 to infinity. So 0 to infinity means it is nothing but half of the minus infinity to plus infinity, isn't it? 0 to infinity is only half. So 1 by 2 times integral 0 minus infinity to plus infinity of this term. So the same idea, power 4 was there. Power 4 was there. I think the answer is this one, not this one. This is the first one answer is copied here. So for this one, there are 4 roots once again. The roots plus or minus, but here we consider only these 2 positive roots. Z equal to e to the power I pi by 4 and z equal to e power I into 3 pi by 4. 3 pi by 4. 1 pi by 4, 3 pi by 4. These 2 are alone lies in the upper half of the plane. Okay, then apply the Cauchy's lemma and Cauchy's residue theorem. You will find the answer pi by 2 into root 2. So these are some problems for your practice. I hope you really enjoy this lecture. If you feel this lecture is good, kindly support for this channel, share comment, like, definitely you subscribe my channel. My channel name is ADC Max. Thank you. Thank you for watching.